My name's Rishabh Batlwar. I'm a research engineer in the research group at Digital Domain. I'm here to represent the entire group and their work that we've been doing in adopting data-driven techniques for various applications in visual effects. And to kick things off, I just want to show a small clip and a small video of what we really do. So at Digital Domain, we believe that we are helping storytellers tell their stories more effectively using the best visuals and the best photorealistic imagery that we create for them. We are there to bring their vision to life, and in the process of doing so, we want to stick to the inspiration that we draw from the real world elements and put them out in pictures and in the kind of compelling visuals that we are trying to create. At Digital Domain, we've been challenging ourselves to rethink of all the old and new problems by taking a data-driven approach or a data-centric approach, so that we can then represent all of these visuals in with such a realistic detail that they would look absolutely indistinguishable from the real world elements. Although we have a lot of different applications that we are exploring data-driven techniques in, a lot of simulation kind of stuff like fluids, fire, smoke, the one that I want to really jump into and talk a lot more about is facial animation. Faces are key to any storyteller's objective. They carry a lot of emotion, they set the drama, they set the tone, and powerful performances really connect well with the audience out there. They're very key to expressing what the story is about and conveying the message that the storyteller wants. So what's important to get out of a facial animation system? The most important things are to get the natural-looking deformations on the face and get all the physical, realistic appearance down to the blood flow, to the pore structure, pore detail, and even the subtle wrinkles that happen on a face. We even go down to matching the subsurface scattering to make the appearance look so realistic that the thing that our eyes and brains are so sensitive to, even the smallest glitches in a facial performance, might completely throw the audience off and create that disconnect that we're trying to avoid. Now, the tough part in facial animation is that the facial motion is so highly nonlinear and has so many degrees of freedom that it's very difficult to really capture all of that motion in a constitutive model or bake that into any kind of equations. It's so organic that going from one expression to the other just feels so natural to us that we don't even inspect what's going on frame by frame. And only when you start looking at this footage at a much slower pace do you realize how much is happening on our faces. And all of these models are very person-specific as well. The expressions that we make that we semantically understand, like smile, being sad, being angry, are very intuitively comprehensible for us, but they're not so easy to transfer from one person to the other. So what I want to really show is a pipeline where we have this multi-view imagery with a marked human face that we can use traditional computer vision techniques to triangulate at least sparse 3D locations from and get this high fidelity result that you see on the right with all of the nice nasolabial folds, the wrinkles, the skin folds, even down to the pore level detail, and something that we want to achieve by very sparse input and get to a result as quickly as possible. So to that end, what I want to do is talk a little about the traditional model that we use for facial animation, and then go on to our exploration of that we've and the pipeline that we've developed now, which uses geometric methods aided with a lot of data-driven techniques to get to this high-fidelity result much more quickly. So the traditional model in facial animation is based on this thing called facial action coding system, which is a thesis proposed by Ekman et al. Back in 1978. What it tries to do is to break a human face down to its bare minimum expressions. So they proposed 50 to 60 primary key expressions that when one puts together, you can create any sort of complex expression that a human face can make. The study was very generic in the sense that they took a lot of subjects, a lot of human subjects, and saw the underlying, based their observations on the underlying facial musculature. And their basis, the shape basis that they provide is very generic and not person-specific. And that's where a bit of a problem lies. Once we develop some primary key expressions for any kind of actor and we start dialing them one by one to make more combination shapes by putting these primary shapes together, we soon realize that the combination doesn't give us the kind of intuitive and semantic expression that we are looking for. And a modeler has to go in and hand correct these shapes to make them better. So what's happening is now these 50 to 60 primary key shapes are then layered on with all of these combinations that are hand corrected. And the sad part is it takes a long time to build up to a much more complex model which can be expressive enough to cover any kind of facial expression that a person can make. So although the result over here that we're seeing is quite good, very high fidelity as well, there are some really nice wrinkles that are coming through. The facial deformation looks very plausible as well. But underlying the animation rig, there are 1,200 blend shapes, which takes quite a long time to build up to and discover the complex expressions that the person is making. So to avoid this entire process of building up to 1,200 blend shapes for a hero character, which comes off as a necessity for representing the realism that we want, we went back to the original input, which is our geometric capture, where we have this multi-image capture and the 3D triangulation of the sparse markers that are placed on the face could then be directly used to drive some geometric model of the neutral face. So what we are doing is we are taking this low-resolution capture, 3D triangulating it, and this is something that we call marker mask. We use a combination of linear and differential geometry operators, most prominently something like Laplacian deformer, to place hooks into the neutral pose of the actor's face and then pull the mesh apart to induce a large-scale deformation on the actor's face. So what you're seeing here is we're going directly from the sparse marker capture, which is the marker mask, to that large-scale deformation that we're seeing on the right. Now, we can take the same geometric approach, and once we've established the correspondence between the actor's face and a CG creature face, We can use similar geometric techniques like use differential geometric techniques to transfer expression by expression the performance of an actor onto the CG creature. So we get results very quickly out of this process, and we didn't have to build any of the fact shapes up until this point. All we had to do was to process a neutral pose for the actor, process the marker mask coming out of the head-mounted cameras. But the problem is that this performance doesn't contain any of the medium-scale details like nasolabial folds, some wrinkles on the forehead, the crow's feet, and any of the high-resolution detail that we are looking for. Apart from that, by showing a few examples, I want to convince you that these deformations are not very true to the person either. Like a mouth wide open shape over here looks so different on the large scale deformation from what the person's face looks like. Over here, we are looking at a result where we are lacking the information around the lip region, so we are not able to recover those lip shapes that we are looking for in the large scale geometric deformation result. Over here as well, we're losing all of the wrinkle information. There are no convincing lip shapes over here. So this is where we really want to leverage the real physical data and induce that or augment this result with that real physical data to get the kind of high fidelity that we're looking for. So in terms of data preparation, we go off and use these more complex camera rigs, which can record at a very high resolution and create a 3D capture of an actor's face while he's performing. These are all offline processes, so they might take a long time for a turnaround. But what we are trying to capture over here as training data is just the extreme expressions of the actor, which would allow us to build a shape space good enough to reach any kind of facial expression that the actor can make in subsequent shots. So once along with that, we are also capturing high-resolution texture maps so that we can then put that back onto the actor's face to show the actor's face in all its glory. And once we have the shape space built, what we are doing is we are going from the sparse marker capture to the large-scale geometric deformation using just geometry processing algorithms. But now the shape space that we built out of the training data is being used to add on some really crucial details like the wrinkles and the skin folds. There are some volume corrections also happening. We are also able to recover some of the parts of the face that weren't easy to capture in the sparse marker capture session. So we see some really great lip shapes. The nasolabial folds are coming through. There are some crow's feet wrinkles that come through the data model as well. And in the lack of for the lack of interest in lack of time, I won't be able to get too much into the details of how we are building this data model. But it's a combination of variants of scattered data interpolation and some other clustering techniques. And I would point you to a publication by our group called Masquerade, which came in SIGGRAPH last year, which covers the technical details of this process a bit more in depth. Some of the corrections that we see on these expressions also include the lip shapes coming through really well. We are capturing the sense of what the actor is making in this image stream that we are capturing. Now, the same data-driven approach can also be used to correct some of the CG creature's performance. Some of the geometric transfers that we did from the actor's face to the CG creature also has some problems in terms of reaching the expression or the kind of fidelity that we are looking for. And Similarly to the actor's face, we create these synthetic data correctives or corrective shapes, which would be used to build the same sort of shape space, but now for the CG creature. And once we run the geometric transfer through this data model or the shape corrective model, we get that extra fidelity that we're looking for in CG creatures as well, to make them look more convincing and more appealing. One more example of where we're using data-driven techniques now is wrinkle map regression, where we have this set of high-resolution texture maps that we can look up into based on what the facial shape of the actor looks like, and then blend them all together to show their contribution and put that on top of the actor's face to show the high-resolution detail that we are looking to recreate. Now, to compare both of the techniques, the facts-based model took several months because of the build process of the expression space that we wanted to represent every facial expression that the actor can make. And the shape space is built very iteratively as well. So we build the shape space, and only when we are not able to capture the kind of expression that we want do we iteratively add more layers of combination shapes on top of the existing facts model. But with the data-driven approach preceded by the geometric approach, we are able to get to a very high fidelity result in a matter of weeks. And the shape space is built from real-world physical data, which guarantees us that we are much closer to the real physical appearance of the actor. And that's kind of the goal that we first set out for ourselves, is to be able to recreate the real physical appearance of the actor. And the data-driven techniques are allowing us to do that now. So as an overview of the entire process, what we have is a markered face input that we are using traditional computer vision techniques to 3D triangulate the markers on the face to get a marker mask, which then drives a neutral mesh using geometric deformations only, getting us the large-scale geometric shape of the actor's face. Once we have the training data, which includes the high-resolution captures and the texture detail, we are able to get to a very high-resolution final model, which is true to the person and has all the parts of the face that we want out of the digital double. So this is what we were hoping to get as a result. We would take the image stream to give us directly a high fidelity actor model or actor shape. And over here, I'm showing another processing of a dialogue where the training data is only covering the the extreme shapes, but now that we built a good enough shape space, we are able to use that training data to process other shots where the expressions are not as extreme, but the shape space is good enough to pull those details out and recreate the face with much more high fidelity. At the end, I want to thank the entire creative team at Digital Domain, the R&D group, as well as the managing team who've been working tirelessly to bring about this data-driven approach to facial animation and other VFX applications that we are developing in-house. Thank you.